Think about that big, white box sitting quietly in your kitchen, keeping all your food perfectly fresh. We plug it in and it magically creates ice-cold air inside, right? Well, actually, there's absolutely no magic involved. What's happening inside is a masterclass in engineering and a flawless thermodynamic dance. In this explainer, we're going to uncover the fascinating hidden physics inside one of the most essential, yet totally misunderstood appliances in our daily lives, the refrigerator. As you'll see, we're going to break down exactly how invisible energy is manipulated step by step. Okay, let's dive into this. Because this right here on the screen is the biggest misconception about the entire cooling industry. Your fridge, it's not a cold-producing factory. It is, in reality, a highly skilled heat thief. Its primary mission is to absorb the heat trapped in the air and the food inside that box, and literally throw it out into your kitchen. You feel the inside getting colder, but what you're actually experiencing is just the absence of heat.
We are literally fighting nature here, guys. According to one of the most fundamental rules of physics, the second law of thermodynamics, heat naturally wants to flow from a hot area to a cold area. It's why a hot cup of coffee forgotten on a table eventually cools down to room temperature. But in a refrigerator, we're forcing it backward. The inside is already cold, yet we want to grab those last remaining crumbs of heat and push them out into a much warmer kitchen. And heat just doesn't flow backward on its own. To perform this incredibly difficult uphill transport, we have to plug the machine into the wall and force it to work using external electrical energy.
Section 1. The thermodynamic cycle. The journey of the refrigerant. So you might be wondering, who are the invisible carriers moving all this heat? Meet the secret agents of the system, specialized refrigerant gases like R600A and R134A. In the past, we used environmentally harmful CFCs, but today's modern gases have an absolute superpower. They can boil and evaporate at incredibly low, sub-zero temperatures. Think about pouring liquid cologne on your hands. It evaporates in seconds, right? And it pulls heat away from your skin, leaving a chilling sensation. These specialized gases pull heat from the inside of your fridge using that exact same logic, just continuously.
Let's move to and see how this builds. This entire operation is a continuous four-step magic loop happening behind the back panel right now. It starts in the evaporator, inside the fridge. The liquid refrigerant absorbs the heat from your food and evaporates into a gas. This heat-loaded gas then travels to the absolute heart of the system, the compressor, which squeezes it with immense pressure. Next, that highly pressurized hot gas is pushed into the condenser, those black coils on the back of the fridge, where it releases the stolen heat out into your kitchen and condenses back into a liquid. Finally, this liquid is squeezed through a tiny expansion valve. Actually, think of it kind of like an aerosol can. It causes its pressure to drop rapidly, turning it ice cold and ready to start the whole loop again.
Now, you really have to pay attention to that compression phase. The compressor takes that low-pressure gas from the inside and squeezes it so hard that thanks to the laws of thermodynamics, its temperature absolutely skyrockets. We are talking about hitting temperatures of 70 to 90 degrees Celsius. No wonder those black coils on the back of your fridge always feel like a miniature space heater. It's radiating that trapped, extremely hot, pressurized gas.
All right, Section 2, Understanding COP, the efficiency equation. Now, what's really interesting about this slide is the math behind this magic. Looking at this simple bar graph, the energy balance here is just fascinating. Check out the equation, QH equals QL plus W. Let's say your system pulls 100 watts of heat energy out of the fridge interior. To do that heavy lifting, your compressor uses 30 watts of electrical energy from the wall. Well, energy doesn't just disappear into thin air. The total heat release from the back of the appliance into your kitchen is the 100 watts pulled from the inside plus the 30 watts used by the motor. That totals exactly 130 watts. This mathematical proof shows exactly why the back of the appliance constantly radiates warm air.
And that brings us to absolutely crucial metric, the coefficient of performance, or COP. When engineers design these systems, they don't just ask, how much electricity does this machine use? The real question is, for every single unit of electrical power consumed, how many units of heat can it successfully move from the inside to the outside? It is entirely about that ratio. That is the golden rule of refrigeration efficiency.
Think about a standard electric space heater for a second. It pulls 1 unit of electricity and gives you exactly 1 unit of heat. But because your refrigerator isn't generating cold from scratch, it's just moving existing heat around, its COP is always greater than 1. What does that actually mean for you? It means for every single dollar you pay on your electric bill, you are getting multiple dollars worth of cooling power. It's literally one of the most brilliant examples of hacking physics to our advantage.
Moving right along to Section 3, maximizing efficiency, practical energy savings.
Now that we have the theoretical physics down, let's step back into your kitchen and look at some crucial everyday tips you can use to manipulate this exact cycle and lower your electric bill. Every single one of these relies on the physics we just covered. What happens if you leave the door open? Boom. Warm, humid kitchen air rushes in, the sensors trigger immediately, and your compressor is forced into an expensive, high-energy overdrive just to pump that massive heat load back out. If the condenser coils on the back are covered in dust, releasing heat becomes much harder, forcing the motor to work way longer. Keeping that rear area clean and ensuring good airflow is absolutely essential for the system to breathe. Your choice of technology plays a huge role here too. Older, classic compressors operate in only 2 modes, full blast or completely off. It's like a car constantly doing stop and go in heavy traffic. It burns an incredible amount of fuel. Modern inverter compressors, however, have variable speeds. They ramp up when you need heavy cooling, but once the temperature stabilizes, they throttle down, idling continuously in a whisper-quiet, low-power state. This vastly reduces energy consumption while maintaining perfectly stable temperatures.
Section 4, practical troubleshooting. Fix it yourself.
And this brilliantly illustrates how, because you now understand the fundamental physics of how this machine breathes, you can actually diagnose issues yourself before calling a repair technician. Take a look at this daily practical troubleshooting breakdown. If the fridge isn't cooling properly, it might mean the secret agent, the refrigerant gas, has leaked out, or maybe the fan pushing that cold air is simply broken. If the back is dangerously hot, the system is struggling to reject heat, pointing straight to poor ventilation or a dirty condenser. Seeing a massive ice buildup? Your automatic defrost heaters have likely failed. And if the machine runs constantly without ever stopping, check those door seals. Your kitchen's heat is probably leaking right back inside.
So, bringing it all together, we come back to the core philosophy of this entire machine. A refrigerator doesn't create cold. It moves heat from one place to another using electricity. There is no winter storm being generated inside your appliance. It is simply a brilliantly designed, closed-loop pipeline where magical fluids transform from liquid to gas and back again, endlessly stealing the hidden heat from your groceries and discarding it into your home.
You now know for a fact that the second law of thermodynamics is unforgiving. If you leave the appliance open, your fridge will just swallow the massive heat of the kitchen, the compressor will draw more power, convert that power into even more heat, and ultimately make your room far hotter than it was before. So, I leave you with this. The next time you want to cool down your kitchen on a sweltering hot day, will you make the mistake of leaving the fridge door open?